Hey everybody. So about 2 years ago now on this channel, I started talking about a concept where I discovered that essentially there's an underlying geometry to data that exists overall. And then to me, when I first started thinking about first discovered these things through flat out just experimentation, like brute force experimentation around these things, uh, it was like out on a limb very much, right? And then I realized that, and then so from that point forward I really shifted a lot of how I talked about things and what I would talk about on this channel, because I realized at that point and at that time that essentially in order to prove those claims out, you're dealing with questions that have very, very deep implications when it comes to physics, and you're dealing with a completely unproven realm of physics overall. The entire concept of this boils down to the eternal question of whether or not the universe is deterministic versus quantum. And that's a big question, right? And it's a big question that has been in existence for a long time. And then within this geometric theory is an implication that when you take this to its end, it is very easy to draw the conclusion when you take it to this full geometric theory to its end result that the universe is quantum and that it completely eliminates the deterministic debate. But that's not entirely true overall, right? And then so this entire concept to me from the beginning of realizing that this is the trajectory that these things are going to go has been a minefield, a landmine. Like, I have personally not wanted this to be true, right? Like, if I could pick anything to be true, like what would be the best trajectory forward for these things, this would not be the path that I would have chosen, right? Because it's uh, it's not monetizable. There's no money in this, and it's the reverse, right? Like um, it, it's the opposite of monopolizable in any way, shape, or form. And then it has massive and big implications for physics that are unproven and that you have to go out on limbs to even talk about. But so now here we are about 2 years later, and then so this paper is like, to me, you're no longer going out on limbs when you're talking about these subjects overall, because here we are, Harvard University, as well as U2IS labs in Paris, and then so overall, um, there's been a sort of a progression within academia when it comes to these things, and that's a big thing that I've talked about and I talk about often on this channel, right? That my problem overall with academia is that it's slow when it comes to these things, right? That it's okay, it works in practice, but like, what is the theory? Like, we have to prove out the theory before we can move forward with the practice, and that's backwards to me overall. And then so where we're at with proving out the theory at this point is still, even though this is Harvard and a majority of it's there's I've shown at this point that there's institutions like MIT, all of the Magnificent Seven, etc., that all support this. We'll call it like a Platonic geometry theory, right? There's like a different names, and you can frame it in different concepts, but like that Platonic geometry is what I see most people referencing around this concept at this point, when people talk about this kind of like on broader terms. And then so they are essentially within this paper proving that this Platonic geometry exists, is real, right? And that there's this concept of a learning space. And then so essentially what they're proving out in this core question, and it's been a question within AI models for a while, is so you feed them just gobs of data, and then do they just memorize the data, or what happens within that? And then within this, it's very clearly proven at this point that they create concepts based off of this, utilizing the geometric projections and the geometry associated with all of this. And then so that's where geometry plays into this concept, is that essentially it's a unifying geometry for concept learning. That how exactly does learning occur? How exactly do you learn about concepts, classify concepts, etc.? It all boils down to and starts with geometry overall. But the big thing that these papers and even Harvard, etc., where academia is missing still at this point to me, and even in this paper. So this paper 100% is every single mathematical equation that is listed within this paper is a Euclidean equation, right? It's operating within a Euclidean universe overall, because to operate in a non-Euclidean universe for these institutions, they couldn't put out a research paper like that, right? That they would have to be, they'd be going a step beyond what they can prove out within this research paper. So they're bounded by that overall, right? Pointing that out. But then, so all of their claims, all of their math, 100% is in utilizing Euclidean geometry. So I'm going to take their exact same paper here, their exact same method, what they're proving out, what I've been talking about for 2+ years on this channel at this point. And then we're just going to do a simple experiment, right, and a simple test. And in this test, it's going to be Euclidean versus temporal geometry, and then it's going to be a minimal learning experiment. And then so this notebook demonstrates with the controlled synthetic experiment that the fundamental difference between static or Euclidean geometry and temporal geometry in learning systems. And the goal is to show visually and empirically that some systems are purely positional and can be solved from a single geometric snapshot. So some problems that are easy enough to be framed within this realm where a model can essentially memorize the problem, whereas other problems are intrinsically temporal and cannot be solved. Sorry, I hate it when I do that. And other problems are intrinsically temporal and cannot be solved from any sort of static embedding, no matter how accurate the embedding is. And then so this mirrors the distinction between the concept cones that they're bringing out within this paper, which are reliant on static and Euclidean geometry, the embedding style representations, versus trajectory or path-based representations, which are temporal and path dependent. And then so as a dataset overview, we generate a synthetic dataset of 2D trajectories, and then each sample is a sequence of 20 points in 2D. Each trajectory is normalized for stability. From each trajectory, we derive two separate labels: the static label, or the Euclidean task, which is essentially breaking it up into 4 classes that label depending on only the final position, whereas the temporal label, or the temporal task, is the overall turning direction of the path. So left turn versus right turn is made into 2 different classes, and then this label depends on the entire history of motion and not just the endpoint. We compare the models together, like it's essentially like the as similar to underlying architecture as possible with regards towards like everything, but just different math, right? Euclidean versus temporal math, and then so that of course shapes and changes the data set overall, but it's trying to keep the experiment like as close and to the same models as possible. Static task results, as far as the quadrant classification, I'll show you here. Both models perform it extremely well, and I'll show you some differences within that. I'll show you the results, and then we'll go through here, right? So here's all the setup, all the code. You can take a look through anything that you like here as far as like all of the math that's being involved for the different models, and then the training and the evaluation mechanisms. And then so first of all on the on the static task, right? And then so with the Euclidean model, it starts off like super good. It starts off the bat at 94% training accuracy, and 75% training accuracy. But then notice here, like the models, like the temporal model is testing higher than the training accuracy. Like it's like that's the point within this, right? And you can see the improvements overall within this training task and over the epochs, especially on both the training and the test accuracy with the temporal model, right? And the temporal model gets up to like 98.6 is the highest, and 98.9 on the test. And then the Euclidean model just starts to like, it starts to overfit. To me, 99.3, 99.7. And starting to memorize the data set after 10 epochs because it's a simpler data set. And also, too, that the Euclidean model is given, right? Remember, the Euclidean model is just given that snapshot. So it's just given that endpoint result in time, whereas the temporal model is like guessing like what's actually happening in the future. And then so it's getting better and better at predicting that. It gets up to 99% on that overall. But then, so this is the more important task, and then the one that I want to clearly demonstrate within this, which is training on the temporal task, right? Which is like essentially like distant left versus right turns, and then that sort of classification. And then so within that, both models start off coin flip, like well, like 50% accuracy, which is not like what. So in this, it is coin flip, right? Because it's two categories, left versus right. So it is one. It's both of them are just coin flipping it, and then that stays all throughout 10 epochs. Like by epoch 10, the Euclidean model is still coin flipping this, whereas with our temporal model, it's getting up to 80% accuracy. Like and it jumps to that to 70% around epoch 5. Epoch 10, it's getting 80. So we could continue this training, right? If we went this and the scaling laws, etc., I would expect that we go to 15 epochs. This would go up to 85% accuracy. With 20 epochs, it'll go up to 90, and it should keep going up from there within this. Whereas the Euclidean, it's just completely flat, right? So 0.502 and 0.503 are epoch 1 and 2, and then epoch 10 is 0.503, which is like literally the same as epoch. It's lower overall, even on the test accuracy, than on epoch 2. So it's just like it's not doing anything, which is like the point and what I want to illustrate within this overall, right? And then so the point to me to illustrate within this and to highlight is that so I'm ecstatic and happy at this point that essentially like academia is catching up within these things and with these things overall, which is exactly what I've been saying should and would, and the people like haters and things like that who have said should and would happen within this, right? That if this is true as to like these theories, and they would play out, and then so here we are. And then so within that, and then within this, I want to dive just a little bit deeper into essentially like that boundary of what this actually means for physics, right? Like why I've been like like really careful with regards towards what I talk about around this overall, because it's important when it comes to physics, right? And so I'm just going to outline here like 100% what my claims are with regards towards physics around this and what they are, right? And then so 2 years ago, I noticed something that completely changed how I look at data. Not a model improvement, not an optimization trick, and not a clever architecture tweak. Something deeper. I realized that there's an underlying geometry to data itself, and that geometry is not Euclidean. At first, I thought that was just a mathematical curiosity, some abstract lens to look through. But the further I pushed, the more uncomfortable it got. Because once you accept that meaning lives in geometry and that geometry is non-Euclidean, suddenly a lot of things that we assume about reality stop being automatic. And then something even stranger happened. I realized that once you take this geometry seriously, you start implicitly tipping the scales between entire competing theories of physics without even trying to. It's just if you think that this is like an experiment that works and you can prove it out, you're literally in the camp of this physics theory, and you have to be in order, and you're disproving this physics theory, and you're not trying to do those things, right? Without invoking particles, fields, or constants, just from information itself and how it behaves. And then so at that moment, I was no longer just doing machine learning, I was studying on unproven physics, like 100% unproven physics at that point, right? And then that's where I made a very hard rule for myself that I'll only argue from what I can prove at all times. And then that's where I started getting very heavy into like these style of videos, experiments, giving you all of the code, etc. overall, right? Because I realized at that point that this is exactly what I'm talking about, essentially like on a daily basis at this point, and at that point is at that point very unproven physics, right? And then so like if I'm going to talk about like here's my exact proof behind every statement behind that, and then so no metaphysics, no mysticism, no like trust me, bro, only falsifiable experiments. And then so what I could prove, and what I could prove is this, that, and what I can prove is this, that some problems cannot be solved from a static snapshot of data, no matter how accurate that snapshot is. And that's where I started within this, right? That like, so if you like, once you get to the point of this within the research, you realize that this doesn't solve for everything, right? You throw problems like this, and it's like, well, I would expect, like, well, like, why isn't it learning like at all? Like it just sucks. Like it's never gonna learn, right? If you're just sticking with a Euclidean mindset within that. But then it's like, well, then if you just you change the math behind it, like it'll learn. Like you could run this for 100 epochs and it would keep learning, right? The two very different conclusions, and then all you're doing is just changing the math behind that. And like if you run this like strictly based off of this Harvard research paper, you're never going to hit this second layer. Like it just doesn't exist to you overall, like plain and simple, right? But then so so that proves to me that some problems can't be solved via Euclidean math, but they can be solved once you treat data as a trajectory through time, not a point but more of a path. And then that's not philosophy, right? That's what the notebook that I'm showing you clearly demonstrates. Static geometry can tell you where you are, and temporal geometry tells you how you got there. And there are tasks where how you got there is the entire signal. And then once you collapse the path into a point, the information is just gone forever. And then this alone is enough to kill a massive assumption that quietly dominates both AI and classical physics, which is that the full truth of a system is encoded in its current state. It's not. The truth can live in the history of the motion itself. And then this is where the physics boundary appears. And at this point, most people instinctively jump to, aha, so the universe must be quantum. But then that slow down. Like to me, you can't prove that overall. Unless you can prove more than I can within all of this, you can't prove overall that the universe is quantum. You can disprove classical deterministic theory, but you can't prove quantum theory. And then so that jump is exactly where people stop thinking clearly. And so there's essentially three different layers of determinism, and then people constantly mix them up. One is like classical snapshot determinant. That's dead, right? So we can disprove this at this point. Given the exact state of a system at time t, the future is fixed. This is the classical Laplacian era view, right? That this is already dead if temporal geometry is real, because my present position doesn't encode your full causal structure, and the notebook proves this overall in miniature. So like, to me, like it disproves that like the universe is based off of relativistic physics as a whole. It doesn't disprove like relativistic physics on any level, right? It just, of course, it works, and you can't disprove that it works. But it's more like it's a snapshot, right? And it's not how the universe actually works. And then so there's only two doors left within that, right? And then so door number two is still alive, which is trajectory determinism, which is that given the full history of the system and the laws, that the future is fixed, right? That if you have like 100% knowledge of every single prior state of the system, and you're literally going through with somehow you would have to prove how you can get that 100% knowledge, because it couldn't exist within the system for every single problem, right? Because we can disprove that with one. So where do you get that? I don't know. Like, that would be a question that you would have to prove within this. So there's very heavy flaws and burdens to prove within it. Like this is a theory that now has like a bunch of bullet holes within it, but it still stands, right? Like, it's not disproven. So your temporal, my temporal model is still deterministic in this sense. If I hand you the full trajectory, the outcome is computable. So temporal geometry does not automatically imply randomness; it implies history dependence. So like, again, it's like this theory is still alive, but theory three is ontological quantum indeterminism, which is still still you can't prove that theory three is the path within this, right? If we're talking from pure academic standpoints, etc. And then so reality itself does not have fixed outcomes, only probabilities. This is where quantum mechanics lives. And here's the crucial truth. So my work does not prove that reality is quantum. It proves that the reality is not snapshot deterministic. It disproves one. It doesn't prove three. So what my work actually forces the universe to be: if temporal geometry is fundamental, then the universe must be one of only two things. It's either a deeply path deterministic, so everything is fixed but only computable from full trajectories and not states, or it's genuinely quantum indeterminate. Number three, even full trajectories only exist as probability distributions. And then so it's one of those two, right? It's either two or three. And those are the only two options left on the table. One is gone, right? We can, so there were three probabilities. We can fully eliminate one. Now there's only two. And then so why does this suddenly tie into academia? While I was stubbornly staying inside what I could prove, something else happened. Inside institutions like Harvard, MIT, and major research labs began formally validating what's I see it being called a Platonic geometry theory, and the idea that concepts don't live in symbols, that they live in geometric structures. Academia is finally co-signing what independent researchers, builders, and engineers quietly ran into years earlier. But here's the thing that no one is talking about yet. If meaning is geometric and geometry is temporal, then physics itself is now being constrained by learning theory and not the other way around. So to me, that's pretty profound. But so the actual boundary that I'm studying on, so here's like the real edge of the map. I can prove that static geometry is insufficient. I can prove that time carries irreducible information within time itself, which has major implications for physics overall. I can prove that state alone is not causality, and I can prove that many learning problems exist only in trajectories. What I cannot prove yet is that number three is 100% true, right? That whether the universe is fundamentally probabilistic or deterministic in a way that no snapshot can ever reveal. And that's the important part of this, right? I can disprove classical determinism, but I can't disprove that the world could be deterministic in a way that no snapshot could ever reveal. And then so that boundary is exactly where physics and machine learning now collide. And then so line I won't cross yet. I personally suspect, if you haven't noticed yet, that the universe is quantum. But I refuse to declare that as a truth without a falsifiable bridge. So instead, I say this, and this is the strongest, honest version, that temporal geometry disproves classical state determinism, like the classical debate around this. but whether it proves quantum indeterminism remains an open experimental question. I can't prove 3 is true, and that is the real scientific boundary, not hype, not branding, not ideology. And then so a clean fault line carved directly by what can be measured. Overall, just like kind of snapshotting it, I didn't discover that the universe is quantum. I discovered that the universe is not a snapshot. And once that's true, physics no longer gets to pretend that time is optional. And that becomes the bigger truth and the bigger part of this equation overall, right? Is that what do you do with that from there? And what does that mean overall to this larger equation? To me, that's the spooky door, right? I don't know 100%, but like it disproves a lot of classical theories when it comes to time, etc., things like that. But so just pointing those things out. And so that's where we are at the moment. That's where Harvard is at the moment. That's where the world is at the moment within these things, right? And then to me, again, like just pointing it out, academia it is going to be the laggard within this, like by about like 2 to 3 years. But you can see that even academia is at the point where they are recognizing the whole holistic concept. They just aren't taking the next leap with regards towards non-Euclidean geometry. They recognize that the manifold exists, but they're still comfortable in the snapshot universe. And then given, I mean, it's a you have to break physics and like as it currently is in order to like even conceptualize these things overall. So it's kind of hard, but I think that they can get there and they'll get there soon. And so I'll leave a link to this research paper as well as this document over here and this collab notebook if you want to look through these things. And if you like this type of content, please like and subscribe. Thanks very much.